Welcome back to Cryptography and Network Security series. In this video, we'll be discussing about the symmetric key distribution using symmetric encryption. So under this, we'll be covering a lot of topics, right from the understanding the definition of symmetric encryption. We'll look into the key distribution scenario. We'll speak about the session key lifetime, hierarchy, key controls. We'll also look into how the transparent key control scheme works, how the decentralized key control scheme works, what is the usage of key usage control, methods to control the key usage, and we'll end with the control vector encryption and decryption. So in this one video, we'll be covering all the topics related to symmetric key distribution using symmetric encryption. If you have not watched my previous videos or checked out my CNS playlist, I've tried covering all the important topics, all the important algorithms in it. Do give it a check and subscribe to my channel so that you don't miss out any of the notifications. So let's get started. So firstly, we'll understand what symmetric encryption is. Okay, so symmetric encryption will involve both the parties to share the same key. That is, here I have the sender and on the other hand I have the receiver. Sender will send the same key, receiver will also get the same key. In this case, when the encryption and decryption process is happening using one key only, in such cases it is called as symmetric key encryption. So this key must be protected from unauthorized access. So frequent key changes are recommended to minimize the impact of key compromise, because with each and every transaction the vulnerability to gain the knowledge of this key becomes more, because the attacker, no, he'll try gaining the insights of the key, he'll try decoding what the secret key actually is with each and every transaction. And if we are using the same key for n number of transactions, then it will definitely be possible for the attacker to decode it sooner or later. So in that case, it is important to minimize it is important to frequently change the keys. So considering two parties A and B achieved the key distribution in the following ways. So we'll be discussing the several approaches for distributing the keys between two parties A and B. So the first is manual delivery. So A can select a key and physically deliver it to B. Next we have is a third party delivery. That is, a third party can select the key and physically deliver it to A. So third party would be there who will deliver it to A. Next we have is transmission of a new key. That is, if A and B have previously and recently used a key, and one party can transmit the new key to other encrypted using old key. So between the sender and receiver, you are sending a new key which is encrypted by using the old key. So this is again somewhat making use of the existing keys, the legacy systems, and then building upon a new key. Then we have fourth one, that is key distribution center. So a third party or key distribution center can deliver keys to A and B throughout the through the encrypted communication links. So if we speak about the manual delivery methods, they are useful for link encryption. But when devices communicate directly with each other, this situation is acceptable. But when we are dealing for end-to-end encryption and distributed systems, especially in the large networks, manually delivering it to each and every node becomes very tedious task, right? And it is impractical also. Not just that, the number of keys required also grow more as the network grows. So it grows with n into n minus 1 by 2 times keys are needed for n hosts or users. So this was about the first and second. Speaking about the third option, option 3 involves transmitting a new keys encrypted with the old ones, and it can work for link encryption, but it has risk. That is, if attacker knows what is the old key, then he can be able to decode the new key also, right? That was about the third option. Next, for end-to-end encryption, some variation on option 4 is widely adapted. So comparing all the other options, we can say that fourth option is slightly better. So we make use of key distribution center for distributing the key to pairs of users or as needed. So comparing all these four methods, we can say that the fourth method is a little feasible. So each user must share a unique key with a key distribution center for the purpose of key distribution. So this is what they've spoken about the key distribution and how it actually works. So here we have the figure, the usage of key hierarchy. Let's now discuss about the use of key hierarchy. So the key distribution system is based on the usage of hierarchy of keys. So here at minimum two levels are used. So if you can see here, there are two levels of hierarchy which are present. We have session keys here and master keys. We'll look into what session keys and master keys are. So like session key is a temporary key which is used during the encryption process. So it is used for the duration of logical or connection such as frame relay connection or transport connection, and then it is discarded once the transaction or the session is completed. Then we have each session is obtained from the KDC over same networking facilities used for end user connection. So making sure that the user and the sender and receiver are connected over the same network, they exchange the session keys for this particular transaction. Session keys are transmitted in encrypted form using a master key that is shared by the key distribution system and the end user system. So in order to get the session keys, they are further deduced by the master keys. So like by making use of master keys, this method will reduce the number of keys that must be distributed, as only master key need to be securely shared in advance, rather than secure keys being shared for each and every time or being shared for every communication pair. So even in large systems, the problem of key distribution is manageable by making use of the session keys and master keys concept. So by usage of key hierarchy significantly reduces the complexity of key distribution in large networks. So that's what I've explained. Next, moving on further, we have the key distribution scenario. So key distribution scenario speaks how the key exchange process happens, process happens accordingly. So here we have the steps. So let's look into this diagram. Okay, so firstly, here we have the key distribution center, here we have the initiator, and here we have the responder. Initiator will send the message and responder will receive the message. So first, user A will send a request message to KDC. So if you can see here, a request message is sent to KDC to obtain a session key for establishing communication with the responder. So in the message, in the request, what all will be there? Firstly, identity of the user A will be there, then identity of user B will be there, and then we'll make use of a unique identifier called nonce. So nonce could be a random number or any unique number which could be generated. But then for each and every transaction, each and every session, this nonce has to be unique. So in that case, random number selection is the best. Okay. So first step is done. So this requests a session key. Now from key distribution center, a response is sent back to initiator or user A. So the key distribution center will respond to user A with a message which will comprise of two parts. This is the first part and this is the second part. In first part, it is encrypted form, right? So in encrypted form, we have KA. So this encrypted part is encrypted using the A's master key, and it will contain firstly KS. So KS means this is the key generated or the session key generated to establish connection between A and B. Followed by that, we have identity of A, then we have identity of B, and then we have the nonce which was generated from the original request. This is the first part. In the second part, it is again encrypted. So this part is encrypted using the B's master key. So we are making use of KB here, right? So only B should be able to decrypt this. So in this, we'll have the session key, the generated session key, and then the identity of A. So this response is sent back to A. Now A will get the session key. Now user A will forward the second part. If you can see, the second part is forwarded here. So because the second part can be decrypted only by making use of the session key or the master key of responder B. Okay. So user A will forward the second part of KDC message, the encrypted part, with KB to user B. Now user B can decrypt this message using their master key, that is KB, and it will obtain the session key and identifier ID A. Right. So this step will make sure that only user B will be able to access the session key because it is encrypted by user B's master key. After encryption, now user B will send a response, right? So user B will send a message to user A, and this response would be in encrypted form, which will comprise of the session key firstly, and along with that, a new message or a new nonce is generated N2. So this step will verify that B knows the session key and adds an additional layer of security against the relay attacks. That's why we have made use of a new nonce N2. Now after that, session initiator A. So user A will again send back a message to user B. Again, it will be in encrypted form using the KS session key. The message will contain a function of the nonce f of N2. So this is the authentication step which will make sure that A also knows the session key and that this message is very fresh. That is, it is not a relay message. So you can see that in step 4 and 5, along with the step 3, they are performing the authentication function. So by making use of nonce N1 and N2, this will help us prevent the relay attacks, and it will make sure that messages are not just recordings of previous communications, but they are generated then and there. Fresh messages are sent. So like overall we can say that key distribution scenario will allow the user A and the user B to establish a shared session securely by making use of the key distribution center. So this key distribution center is trusted by both initiator and responder. So the master keys are shared between each user, and the KDC are not exposed to it. So only the session key which is used to secure the communication is distributed by KDC. So yeah, this was about the key distribution scenario. That's what I've explained, and I've written down here all the points. Next we have hierarchical key control. So for a larger network, instead of relying on a single KDC, it can create a hierarchical key control system. So from one KDC, it can be further sent to the another KDCs, and thereby it could be sent to the respective users or responders accordingly. So here in this structure, local KDCs can handle the key distribution within their domains. If it is within their domain or the LAN communication or the single building, at that time we can make use of a single local KDC, while global KDCs can be used for inter-domain communication. So inter-domain communication could happen by making use of the global KDCs. So this system will help to scale the key distribution, and it will minimize the impact of compromised KDC to the local area, thereby providing more robust security. More robust security in large networks. So this hierarchical concept can be extended to many layers depending on the size of number of users and the geographic scope of internet work. So this was about the hierarchical key control. Next we have is a tiny topic called session lifetime. So the session of the session keys, the security of the session keys increases with their frequency of change, because if attacker has less time to compromise the key, then it is more safer, right? So here the more frequently session keys are exchanged, the more secure they are, because attacker has to capture session key every time to decrypt a cipher text. So in summary, you can say that shorter the session key lifetime, key exchange frequently, it will be more secure. Thereby it will be very difficult for the attacker to decrypt it. If the session key lifetime is large, then it will reduce the key exchange time and less network bandwidth will be there, and in that case there could be some chances for the attacker to take time and decrypt this session key. So in connection oriented protocols, new session key has to be generated for each connection, and it has to be update key periodically if connection has long time. In case of connection-less protocols, user use session keys for limited period or certain number of transactions to balance the security and performance. So here again we have spoken about the connection-oriented and connection-less protocols. We'll be looking into this in the upcoming videos. So let's get started with transparent key control scheme. In previous videos, we have covered about the other key control or the key usage schemes, right? Like symmetric encryption, key distribution scenario, and all of that. Here we'll be discussing as to how the end-to-end encryption happens over a transparent medium, where both the users get to know what transaction or what communication is happening. Okay, so this scheme provides an end-to-end encryption for communication at network or transport layer in a way that it is transparent to users. So here it makes use of the session security module, SSM, and works well with connection oriented protocols like TCP. So here we'll look into the step by step how it actually works. Okay, so at the first step which we have here, host A wants to establish communication with the host B. Okay, so first host A will send a communication request to the packet. Okay, so it'll reach to the security service. So here the packet will contain the information which is necessary to initiate the communication. Here the session security module SSM of host A will intercept and temporarily buffer the request here. Next, at the second level, if you can see here, the SSM applies to the key distribution center KDC for permission to set up the connection. So here the request is encrypted using a master key shared between the SSM as well as the KDC. This will ensure that secure communication is happening between these two. Next, after that, there is a response sent back. Third step, So if KDC approves the request, it will generate a one-time session key KS, which will be used further. The KDC will securely distribute the session key to the SSMs, this SSM and this SSM also, and on the both sides, that is host and receiver, making sure that it is like using the unique permanent keys that each SSM will share to the KDC accordingly. Next, after that, fourth step is to establish the connection, right? So once the session keys are distributed, SSM of host A, so it had buffered the packets, right? Now it will send the packets here to host B, and a secure communication is now established between the host A and host B with all subsequent user data encrypted using the session key. So buffered packets are transmitted here. So that's what I've written down here. All the steps have been specified here. Connection setup. So the first step was connection setup. Then we had the session key request, session key distribution, and this was the final connection setup between the sender and the receiver. So we can say that this represents the it makes use of the application layer to initiate the connection and send the data, and it makes use of the network layer to transmit the encrypted packets between the hosts. This method supports dynamic and flexible key distribution for multiple hosts and multiple users. Next, we have decentralized key control. So in decentralized key control, there is no central KDC. So instead of central KDC, each system will directly communicate with other nodes to establish the session keys. So this approach is suitable for small network, or if it's like 1-2 users in a given network, this could be used, because without the use of key distribution center, it becomes very difficult to share the keys, right? Keep a proper track of how keys are being shared and all of that. So here we have the figure. So this first step is, user A will send a request to user B, and this request will have the identity of the user A. Along with that, a nonce N1 would be there. N1 is a random number which is used. So this N1 will make sure that the request is unique and it prevents any relay attacks if such relay attacks happen. Next, a response would be sent back. So this response, this user B will select a session key firstly, KS, and he'll encrypt a response using the shared master key. Shared master key here is KM, and this response is encrypted here. Okay, so this shared master key is between A, initiator, and responder A and B. The response here will comprise of KS, that is the session key or a temporary key for secure communication, ID of A, identity of A, and then ID of B, that is this identity of B will help A to confirm that the message is from B only, it is not from anyone else. Then we have F of N1. F of N1 is transformed nonce. So this will ensure that B has received the message, B has received the request, and he has processed the A's request and sent back a response in the form F of N1. He had got N1, he processed the request, and he has sent back F of N1 to the receiver. Next, along with that, we have N2 also. N2 is the new nonce which will challenge A to confirm its authenticity. In order to confirm its authenticity, it will further give a response back. That is the confirmation step from A. In the confirmation step, user A, it will make use of the session key KS, and A will respond back to B with a transformed version of the new nonce which was sent by responder B. That is F of N2. This is the new version. So this step will make sure, ensure B that A received the session key whichever he sent, and the session key and the communication is not a relay connection. So this will confirm that session key exchange has happened properly. So if you compare to the centralized one, here we are not making use of any master key, and the session key distribution happens like directly between the systems, but this is very practical. This is practical only for the small or local networks, and trust is among the distributed systems here. Compared to the KDC, the trust was upon the KDC, right? So but here it is among the systems. A has complete trust on B and B has complete trust on A, and that's how it actually works. So here I have written down the explanation. Next, speaking about the importance of key usage control. So the concept of key hierarchy and use of automated key distribution techniques greatly reduces the number of keys that must be manually managed and distributed. So each and every time when the user is when user A and user B are setting a communication, each and every time if I have to generate the session key, it becomes a tedious task. In that case, automation of such key distribution or the session key distribution is very useful, right? It could be it is better than manually managing and distributing it. It also may be desirable to impose some control on the way in which automatically keys are being distributed. It is very important to regulate how the keys are being distributed here. So based on purpose, session keys are categorized as, so we have three categories of session keys. So first one is data encryption key. So data encryption key is used for general communication encryption across a given network. Then we have pin encryption. So pin encryption is used for securing the personal identification number, pins, for performing the financial transactions and all. Then we have file encryption. File encryption is used for encrypting the files which are stored in publicly accessible locations. Next, we have risk of improper key usage. So if keys are not properly used, for example, if master key is imported as data encryption key, it is against the control system, against the rules, right? Master key should be used to initiate the establishment of session key distribution, not to distribute the data here, right? Encrypt the data here. So in such conditions, master keys are usually stored securely with cryptographic hardware. And coming to session keys, though they are encrypted with master keys, and they are exposed to application programs for encryption tasks. So if master key is treated as session key, an unauthorized program might gain the plain text access to the session keys, which will undermine or break the encryption system. So it is very important to make sure that proper keys are used for proper usage. Next, we have the methods to control how the key usage happens. So the first method we have is using the 8-bit tag. So this is a very simple mechanism which is used to associate a tag with each key. So for each key, there'll be a tag associated. Okay. So this tag will be of 8 bits. So again, 8 bits are like this. Okay. So this tag, this will help us to restrict the usage of the keys. Okay. So for example, for DES keys, extra 8 bits in the 64-bit DES key are used as tag here. So here we have how the 8-bit structure or the 8-bit tag comprises of. So the first bit, 1 bit, will indicate if the key is a session key or a master key. Next, one more bit will tell us if the key can be used for encryption or not. Next bit will tell us if it could be used for decryption or not. And rest 5 bits, they'll be used for they'll be reserved for future usage. So these tags are embedded in the key and they are encrypted along with the key itself. So they will make sure that there is secure distribution happening throughout the process. Next, looking at the drawbacks. So speaking of the drawbacks here, first one is it has limited flexibility. That is, 8-bit size restricts the functionality, and it has operational limitation. Operational limitation means since the tag which we are using is encrypted, it can be only used after decryption. It cannot be used before decryption, thereby limiting the operations. Next method we have here is control vector scheme, or this comes under the control vector encryption and decryption. So a control vector is more flexible approach to control the key usage, as it provides detailed and unrestricted way to impose the control, and it is cryptographically coupled with the key. Okay, we'll see what key is being used and all. So the control vector will have a set of fields which will specify the key usage restriction and grant the permissions, and also have a variable length. So variable length is definitely we are overcoming the drawbacks which we saw in the 8-bit tag, right? So we'll look into the mechanism how it works. So here we have the control vector encryption and decryption, which make you, so here the control vector is combined with the key for using the cryptographic techniques during the key generation. So the first step which we have is the input vector here, input control vector. So the control vector CV is processed through a hash function. It is given input to the hash function. Hash function will produce a fixed length hash value, capital H. Okay, so now this capital H is performed, XOR operation is performed with the master key. So capital H and master key XOR operation is performed, and the session key KS is encrypted using the combined key input. Now the ciphertext output is encrypted using the session key here. So here we have the encrypted session key. Looking at the decryption process, so the first step is we'll take the input encrypted session key. So we'll take the input encrypted session key, and the encrypted session key and the control vector are provided as inputs. So here we have, and here we have two inputs. And then we have CV. So CV is hashed, and the hash value capital H is XORed with the master key. And then whatever the key input we get is given to the decryption function along with the encrypted session key or the ciphertext input. Next, we get the session key as output here. So using the key input, session key KS is decrypted here. So if you mathematically see, this entire part is for the encryption process. So here you are calculating the hash value, H, capital H, fixed length hash value, capital H, and after that you are calculating the key input. Here key input, this part you are calculating it here, XOR operation, and after that you are calculating the cipher text. Coming to here, the decryption process. So you are decrypting whatever contents you have got along with the encrypted text here, and here you are just performing the XOR operation with the input as well as the hashed value. This is for decryption process. Speaking about the advantages, first one we have is unrestricted control and flexibility. So unrestricted control flexibility means the control vector's length is not limited. So it can be like flexible. It can also deal with the complex rules here. Next, it is clear from availability. That is, control vector is always available in the plain text. So this will allow the key usage control at multiple stages. Then we have cryptographic coupling. So here the session key and its control vector are cryptographically tied. That is, they will make sure that key can only be used as intended, not that flexible. Okay. So this was all about the control vector encryption. In this video, we have covered a lot of topics. So if you have any doubts, do let me know in the comments and stay tuned. Thank you.